What is the speed at which no side force due to friction is required for a car traveling at a radius of 240 meters on a 20-degree banked road? Let's begin with an illustration. We have a car that is driving in a circle, and the road makes 20 degrees with the horizontal. So here's a plane that is 20 degrees from the ground, and we have a car that is driving on this plane. So that's my attempt of drawing a car. Those are its headlights, and that's the cabin. To answer this question, we'll be using Newton's second law, which is F is equal to mass times acceleration. This car is exerting a downwards force due to gravity, and it is directly down like this. This vector can be broken down into its components. You have its x component or horizontal component and its vertical component. And adding up these two vectors will give you the magnitude of the downward force. In addition, there is a normal force, and that is perpendicular to the plane and going directly up. So perpendicular to the plane means that it's at 90 degrees, and I'll call it the normal. And this too can be broken down into its components, its vertical and horizontal components. Now, in order for this car to stay still at this particular radius and at this angle without a force due to friction, two things need to be met. The first thing is that the force due to gravity must equal to the upwards force of this normal vector. So if we represent this mathematically, we can replace A with G, which represents 9.8 meters per second squared. Let me write that in. So the force due to gravity, I'll write the subscript G, is mass times gravity, and you can replace G with 9.8 if you like from here. This needs to equal to the magnitude of that vector. So now we have to write down an expression for that vector. We will in a moment. The other thing you have to consider is the centripetal force must equal to the x component of the normal. So remember, centripetal force is equal to the mass of the object times the radial acceleration, which I'll denote as A sub rad, or you can denote it as A sub c for centripetal acceleration. And this can be found by taking the velocity, raising it to the power of 2 over r. So this must equal to m times v to the power of 2 over r. We need to find out an expression for that and an expression for that. How do we do that? Well, first of all, remember back in elementary school that if you have two parallel lines, let's say that's parallel, and it's parallel with this, there's a rule with parallel lines called alternating angles, whereby if that's 20, so is that. So the angle that this vector makes with the purple plane is 20 degrees. Before I continue, let me clean this up a little bit further. Okay, now that I've taken the car out of the way, you can kind of see what's happening. So if this is 20 degrees, then the angle that this makes is 70 degrees. And the angle that is made between this vector and that vector is also 20 degrees. So we have a lot to work with. Let's start by creating an expression for this vector. We will be using trigonometric functions to do that. Remember, the trigonometric functions are sine, cosine, and tangent. We are looking for that vector, and if we use cosine relative to this 20 degrees, cosine represents adjacent over hypotenuse. The hypotenuse is represented by the letter n. Let me write this down. So cosine theta is adjacent over hypotenuse. The hypotenuse is represented by n, so that's the magnitude of this vector. And all we have to do is multiply both sides by n to get the expression for the magnitude of that vector, which is n cosine. I will make this m times g equal to n times cosine theta. This equation right here represents how the vertical component and the downwards force due to gravity are equal. Now, like I mentioned before, there's something else that you have to keep in mind. You have to make sure that this is equal to this vector's magnitude. And for that, we can use sine. So much the same way we did it here, it will be n times sine theta. So this part is equal to that. And from here, all we have to do is solve. We have to solve for v because that's the speed. To solve for v, we need to use some mathematical skills, and one of which is substitution, solving by substitution. I'll solve for n in this equation and then substitute whatever that is into here. Solving for n, I have m times g over cosine theta. Notice that I divided both sides by cosine theta to eliminate this cosine on the right side. And now I will take that and bring it right into there. So I have m times g over cosine theta, and that's being multiplied to sine theta, is equal to m times v to the power of 2 over r. Luckily, this m and this m will cancel out because they're on both sides, so dividing both sides by m gets rid of them. Sine over cosine is an identity for tangent. So you can replace sine over cosine with tangent theta if you like. It's not necessary, but you could. I'm choosing not to, so let's just leave it the way it is. And I'll multiply both sides by r because remember, I want to solve for v. I have g times sine theta over cosine theta times r. This r and that r cancels out, and that's equal to v to the power of 2. And of course, we square root both sides. Square rooting both sides makes the right side only v. Now let's substitute all of the things that we know. We know the radius is 240 meters and it's the right units. Should be in meters. And the velocity should also be in meters over seconds. So 240 will be replaced with r. G will be replaced with 9.8 meters per second squared. Don't write the units down, just keep that in mind. And sine theta over cosine theta. We're told that it's 20 degrees, so I'll replace theta with 20 degrees. And let's use our calculator. The square root of 9, and make sure that you put everything at the top in parentheses. So 9.8 times, your calculator needs to be in degrees, times 240. So that's the top part, and the bottom part is cosine 20 close. We get a velocity of 29.258, 29.258 meters per second. Now, if we want this to the correct number of significant figures, you can simply write down 29 meters per second. And there you have it. That is how we can relate the speed of a vehicle driving on an incline with the normal force and gravity.